Why, hello. We are going to continue the notes for the Unit 3 Derivative Review Unit. This is part 3. Man, it's a good one. But it's important because derivatives are the backbone of calculus. Love it. Let's get going. This is where we left off. Find the derivative of g of t, which equals tangent of 5 minus sine of 2t. Now, we've learned the derivatives, or we've relearned and reviewed the derivatives for trigonometry, and we've started to really talk about the chain rule. We are going to do that multiple times here. Let me explain. When I see this, I know for a fact that I'm going to take the derivative of tangent, and everything should stay the same in here. Okay, my 5 minus sine of 2t times the derivative of the inside. All right, so when I take the derivative of the inside, I'm going to have to take the derivative of sine, okay, leaving the inside of sine the same. Then afterward, multiply that times the derivative of that inside. Yeah, crazy. Let me just go at it right now. So the derivative of tangent, I know for a fact, is secant squared. So I'm going to say g prime of t equals secant squared. The inside stays the same. 5 minus the sine of 2t. All right, times the derivative of just the inside. I'm taking the derivative of just this. Now, the derivative of 5 is 0, so I know that's going to go away. So I'm going to do this off to the side here. 5 minus the sine of 2t. If I take the derivative of this, well, 5 goes to 0. And the derivative of negative sine of 2t is negative cosine. Okay, and the inside stays the same, 2t, times the derivative of the inside, which is 2. So I've got to do the chain rule here and from when I first started. Okay, so I have to do the chain rule twice. Okay, so now the derivative of my inside is negative. Okay, I'm going to take, this is like negative 1 times cosine. If I multiply negative 1 times 2, I get negative 2. So I'm going to call that negative 2 cosine of 2t. And I'm going to write this all together. That would actually be an acceptable answer if you came up with that. However, all right, however, if this were multiple choice, they like to write sine and cosine before they write secant and cosecant. So I'm going to put that up front. And any constants, all right, this negative 2 is a multiplication as well. Any constants they like to put right out front. So I can say that is negative 2 cosine of 2t times secant squared of 5 minus the sine of 2t. Bam. Great answer. Love it. You did fantastic. Look at you go. And again, this would be a good answer if they didn't ask you to simplify. Or if they did ask you to simplify or multiple choice, this is also a really great answer. If you wrote it like the second way, it makes you look like you know what you're doing. But the first way is completely 100% correct. You're good to go. All right? Pachow! Okay, implicit differentiation. Let's review this. When you can't get y equals alone, okay? When you have two terms, both with y's, that you cannot combine, you need to use implicit differentiation, all right? So what we do is we take the derivative of x and y. We take the derivative of y and treat it just like it's x, okay? Except when you take the derivative of y, you need to put dy dx next to it. Or you can do this y prime, but a lot of the times people write this real quick and it looks like y to the power of 1. And I've seen students like mess that up, especially when they're doing a lot of work. It's very frustrating. I see some students just put dy next to it, which is fine, but technically you're taking the derivative of y with respect to x. So I'm going to use this because that's the proper way to do it. And you should do it the proper way as well. Okay, so whenever I take the derivative of y, okay, I need to put dy dx right next to it. And then I end up just solving for dy dx. Like I need to get that alone. So I'm going to have dy dx equals da 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 da, and that's going to end up being my derivative. All right? So let's get started. Let me give you an example of what I'm talking about. Find the equation of the line tangent. Okay, anytime I see this, I automatically think y minus y1 equals m times x minus x1. Equation of a line. That's this right here. Okay, so find the equation of a line, equation of the tangent line to the ellipse x squared minus xy plus y squared equals 7 at the point -1, 2. Now, I know for a fact I need 3 pieces of information for my equation here. I need an x and a y, and then I also need an m, okay? The beautiful thing about this is that they already give me an x and a y, okay? So I have my x1 and y1 here. Please, 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 they go into the x1 and y1. I've had students put them in for these x's and y's. No, those stay the same. So I have y minus my y1, which is 2, equals m, which I still don't know, and that's fine, times x minus x1. What happens when I subtract a negative? It turns to a super positive. All right, so the only thing left here to find is my slope. And if we're using implicit differentiation, that will be the bulk of the work for this problem. Okay, slope, do this in a different color. Slope is the same thing as derivative. Okay, so keep that in mind. So I need to take the derivative of my equation. Here's a problem. I have y squared here. I have y to the power of 1. I can't make this so that it's y equals something and then just take the derivative of whatever is over here. I cannot do that. I need to use implicit differentiation. Here's what we need to do. The derivative of x squared, well, that's just 2x. Okay, I've got to use the product rule here. Okay, this is negative x times y. So it is the first, negative x, times the derivative of y. Okay, I take the derivative of y just like it is in x. Okay, the derivative of x is 1. The derivative of y is still 1. So times 1. But anytime I take the derivative of y, I need to put dy dx next to it. Okay, so product rule. First times the root of the second plus the second, which is just y. I'm writing y. I'm not taking the derivative of y this time. I do not need to put dy dx there. Okay? So the second times the derivative of the first. The derivative of negative x is -1. And here we'll do this. So, okay? Plus 2y, or excuse me, I'm giving you the derivative there. Y squared. The derivative of y squared, I handle it just like it's x squared. It's 2y. But I took the derivative of y, correct? So I need to put dy dx next to it equals the derivative of 7 is 0. Okay, so and for the sake of color, let's do this here so we can figure out where each derivative came from. And then let's keep on going. The derivative here, 7, should equal 0. Good, now it's color coordinated. So now I did the first step. The second step is I've got to get dy dx alone. I'm going to show every step along the way. I could kind of shortcut this, but hey, we're reviewing. So let's simplify this first. I have 2x minus x dy dx. Okay? Plus, ooh, no. Right here is minus y. Y times -1 is negative y. Plus 2y dy dx equals 0. I need to get dy dx alone. So I'm going to keep everything with a dy dx, this term, and this term. I'm going to keep them on this side. I'm going to get rid of my 2x and my negative y. Okay? And I'll show you how, in a second, this is relevant. So minus 2x plus y. minus 2x plus y. All right, good. I now have minus x dy dx. Okay, that's this. Plus 2y dy dx equals negative 2x plus y. All right, good, good, good. I'll do the line there to separate it. Good, good. It's good. All right, we're going here. Now, if you look, I now have a common factor, and I'm going to have to factor out my dy dx. Both of these have dy dx that I'm going to factor out. If I take out dy dx, that leaves me negative x plus 2y, and that equals still negative 2x plus y. In order to get dy dx alone, I'm just going to divide by negative x plus 2y. Okay, this cancels with this. I got dy dx alone. What I do to one side, I have to do to the other side, okay? So this right here now equals dy dx. This is my slope. Most of the time with calculus, when we find the slope, we have an x value to plug in, and we plug it in and we get our number. But here I need an x and a y. If only I had an x and a y. I do. It's right here. My x is negative 1 and my y is 2. So I want to figure this out. Oh boy, too much. At negative 1, 2 for my x and my y to plug in. So that's exactly what I'm going to do. I've got negative 2 times my x, which is negative 1, plus my y, which is 2, all over negative x, which is negative 1, plus 2 times my y, which is 2. Okay, all I did was substitute in for my x's and y's up here, because that's going to give me my slope. All right, well, I've got negative 2 times negative 1 is positive 2 plus 2, all over negate a negative, super positive. Okay, so it ends up being 4/5. That's my slope. That's my slope. That's what I'm going to put all the way back here, 4/5. Look at all that work. And it's brilliant because it's right. That's 4/5. We have our x plus 1 equals y minus 2. And that is an equation of a tangent line at the point negative 1, 2. Now, if they said make it y equals form, just add 2 to both sides. I can do that. I could say y equals 4/5 x plus 1 plus 2. This is also acceptable. Okay, what if they said give me y equals mx plus b? Well, I can just distribute my 4/5 and then add 2. I can do that. I'm not going to. Okay, but I could do that and you'd be fine. Ah, jeez. Let's do it. If I distribute these, I get y equals 4/5 x plus 4/5 plus 2. 2 is the same thing as saying 10/5, right? Isn't that 2? So now I can combine these two. Y equals 4/5 x plus 14/5. It could be written like this, but I'm telling you, unless they tell you to simplify it, leave it like this, because you will be good as gold. It's good work. Now, let's find y double prime, okay, the second derivative, and we're going to have to do it implicitly, okay? I could technically try and do a square root and get that y alone, but let's use implicit differentiation to achieve second derivative, all right? So in order to find second derivative, I first need to find my first derivative, right? So that means I've got to find the derivative of this. I cannot get y equals alone, or I can, but it might be a mess. So I'm going to do this implicitly. The derivative of 2x cubed is 6x squared minus the derivative of 3y squared is 6y, but every time we take the derivative of a y term, we have to put dy dx next to it, and it should equal the derivative of a constant 8 is 0. This is much easier. I'm going to take, and I'm going to get dy dx alone. I'm going to isolate it. So let's subtract 6x squared from both sides. Badoosh! I get negative 6y times dy dx. Kills me to write that every time, but you have to. Equals negative 6x squared. Now, in order to get my dy dx alone, I just got to divide by negative 6y. Gadoosh, gadoosh, gone, bye-bye. Meine divided by negative 6y. So dy dx equals, okay, and I could simplify this. My negative 6's can cancel. So it's x squared over y. This is the first derivative. They want the second derivative. Okay? That means I need to take the derivative of the derivative. Quotient rule, low d high minus high d low, draw a line and square below. That is my low times the derivative of my high minus my high times the derivative of low, and then I square what's below. Of course, my high is x squared, and my low is y. So let's do this bad boy, shall we? Let's do this in purple. Low times the derivative of high is x squared. Okay, well, it's 2x. All right? So y times 2x minus high, just as it is, x squared, times d low. The derivative of y is just 1, okay? But anytime I take the derivative of a y, it's 1. dy dx needs to be written next to it. So 1 times dy dx is just dy dx. All over, and then I square the bottom. This is y, so I square it, okay? This is my fraction I'm working with, okay? Show me what you're working with. Okay, anyways, sorry. I got, I got distracted with some hippity-hoppity. Now, here we go. Let's kind of clean this up. 2x times y is just 2xy minus x squared dy dx all over y squared. Here's the problem. I can't leave this in my derivative. If I only knew what dy dx was, I could substitute in. Oh, I do. Dy dx is equal to x squared over y. So wherever there's a dy dx, I'm going to substitute. Oh, I can't do that now. Oh, boy. I'm going to substitute x squared over y. That's going to go in right here. So let me rewrite that. Okay, so I've got 2xy minus x squared, and substituting in for dy dx is its equivalent fraction, x squared over y, because x squared over y is the first derivative. And right here, you need the first derivative. It's telling you, okay, all over y squared. All right, that is the second derivative. Now, that's a great answer for short answer. If they say find the derivative at some random point, like at 2, -3, then I plug in my x and y to find it. That's fine. They don't here. But if this were multiple choice, and I can't remember if this was multiple choice, or I looked at the answer key, and the answer key was written differently. They don't like having fractions within fractions. So what I'm going to do here is, in order to get rid of this y, I'm going to multiply this by y. Okay? I'm going to multiply the whole top by y. What I do to the top, I must do to the bottom. So this y is going to distribute into this whole first term, and that's going to distribute into this term as well. Okay? So let me write that another way, which might be easier for you to see. I'm going to multiply every term by y. Okay? So when I multiply these two together, I get 2x, y times y is y squared. When I multiply this times this cancels. Minus, okay, x squared times x squared is x to the fourth. All over, when I multiply these two together, I get y cubed. This would be a short answer, okay, or excuse me, a multiple choice answer solution. Without the y's here, what we had here beforehand would be perfectly acceptable, as I said before, for short answer, okay? This is just simplified, all right? Very good. That's good work. That's, I mean, I don't want to say complicated, but you really need to keep track of what you're doing. And if you do, you'll be fine. Be patient with it. Be patient with it, okay? Derivatives of inverses. I used to hate these when I would do things the long way, but now I actually like doing them because they're pretty simple. So the derivative of the inverse can be written one of two ways. Okay, instead of saying y dy dx, it's d of f negative 1 because negative 1 denotes inverse. Okay, that right there means inverse. Okay, or I can just take the derivative of the inverse of f of x. Okay, either way. Now, just by saying derivative of the inverse, that helps you memorize how to do this. It is 1 over the derivative of the inverse, okay? It is 1 over the derivative of the inverse. The way it's said is the way I solve it. That helps me solve it. So it's just 1 over the derivative of the inverse, okay? That's how you are going to find the solution when they ask you for this, all right? Let's apply this to a problem. Badoosh. If S is the inverse of F, so S is f negative 1 of x, okay? And f of x is x cubed plus x. Find s prime of 2. If they're saying s prime of 2, that's like saying s is the inverse, right? They want you to find the derivative. Okay, this is the derivative of s, which is the derivative of the inverse of x at x equals 2. Or better yet, we can do this. I know it's confusing how I'm trying to convert these, but I'm just trying to show you what this means, okay? So we're basically saying find the derivative of the inverse of f at 2 because s is the inverse of f. This is the derivative. So find the derivative of the inverse of f at 2. Bam, there it is. So I need to, in order to solve this, 1 over the derivative of the inverse at x being 2. All right? All right, so let's do this one at a time, okay? This is the way I like to do this. This is very organized. It's methodical. There's a method to the madness. I'm going to first figure out what this is. And whatever number that is, I'm just going to input that right here, okay? I'm going to get rid of this funky notation by solving for that. So I'm going to say, well, all right, f negative 1 of 2 equals something, right? So how do I figure that out? If you remember anything about inverses, that flips the regular equation. Okay? Which means here's the regular equation, here's the inverse of it. Inverse just flips x and y. So this becomes my solution, and that becomes the input. So basically, what value of x do we have that would make our original equation equal to? Okay, let me say that one more time. My inverse is just a flip of x and y of the original equation. So if my original equation, okay, let's say f of 7 equals, and I'm not talking about the one they're giving us, I'm just randomly making up numbers here, is 6. Okay, my x would be 7, my y would be 6. For the inverse, when I plug a 6 in for x, it would equal my 7 for y. So these literally flip when I go from regular to inverse and vice versa. You see what I'm saying? That's just a basic rule for inverses. And that's what I'm going to apply here. I have the inverse. So what about my regular equation? Well, I'm trying to find out what input would give me 2. Okay, because that will help me backtrack and then find my inverse solution here. So my original equation, x cubed plus x cubed plus x would equal 2. So what value of x would go right here to solve for this? Because once I know that value of x, that would flip and become my solution here. Okay? So here we go. You could do this with a calculator, but a lot of the times they'll give you a problem like this, and they won't give you a calculator. So I got to look at this logically. Well, 1 plus 1 is 2. So x equals 1 here. Okay? So therefore, if this x right here has to be 1, then guess what? This value here has to be 1 as well. So f, the inverse of f at 2 is 1, which means this whole value is 1. 1 over f prime of 1. Okay, so now all I got to do is take the derivative of this, find f prime, and put a 1 in. So the derivative of f of x is 3x squared plus 1. I took the derivative of this. Now, if I want to find the value of 1 of that, 3 times 1 squared, which is 3, plus 1, that's 4. So this value here is 4. There it is. Yada, yada, yada. Good. Not too shabby. All right? Last one, derivatives of trig inverses. You just got to know these. This one right here is very common to use. They use tangent quite a bit. Every once in a while, they'll try and sneak in a cosine. But you just got to know these. Memorize secant, cotangent are hardly used. Sine and tangent are the most commonly used. You've just got to recognize the form when you see it. Okay? And last but not least, common. The derivative of e to the u is e to the u times the derivative of whatever u is. Okay? Whatever the derivative of this is, you multiply it by. Chain rule. The derivative of ln of u is 1 over u times the derivative of whatever u is. Okay? And a to the u and log base a of u aren't that common. They are there, right there. Math is an integral part of life. That means integral. That's what makes this funny, because it's true. All right, I think that's it. Yeah, so bang, 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 bang. Click that like button. Someone told me I got to start saying ring the bell. I don't know what the hell that means, but do it, whatever it is. Just don't do anything, that'll get you arrested. All right, see ya. Have fun. I'll talk to you later.